So we have not, we have and we have or. You remember how I said that you can read this as P or Q? Or you could also read it as P inclusive or Q. That's because there is an exclusive or. So that's our next logical operator, which I will define right over here. This is the exclusive or, sometimes written XOR. So the definition of this is if P and Q are propositions, then P XOR Q is true This right here is true if P is true or Q is true, but not both. So this little thing right here, the way that we read this is you read it as P XOR Q, or you could say P exclusive or Q right here. And once again, using a truth table is going to be helpful to understand the definition of this particular logical operator. So the truth table for XOR would look like the following. So we have P, we have Q, and we have P XOR Q right here. So let's go ahead and take a look at what this truth table would look like. So once again, filling in all of the possible values of my variables. Let's go ahead and check out this definition here. So, exclusive or. It's true if P is true, okay, well, in this first row, P is true, and, well, Q is true, but not both. So in this case, this right here would be false. So exclusive or is false if it happens that both of the variables in that compound expression are true. Here, well, it's true if, well, P is true, and, oh great, okay, Q is false, so it happens in this case that P XOR Q is going to be true. False and true, well yeah, one of them is false, not both of them are false, so this here is going to be true. And lastly, we have false and false. Well, P's not true, Q's not true, and, well, they're both false, so this here is going to be false here. So it might help to look at a couple of further examples to illustrate this exclusive or right here. So let's go ahead and look at an example. So in this particular example, let's go ahead and define this following proposition. So I'm going to define the proposition as my name is David. And as you saw in the introduction video, yes indeed, my name is David. My name is Sam. That's a proposition, declarative sentence right here. If you're applying it to me, then this particular proposition has a truth value of false. My name is not Sam. And our last proposition right here, R, is going to represent the proposition PSU or Penn State offers Computer Science 360. By the very fact that I'm creating this video proves that yes, indeed, R has a truth value of true. So let's go ahead and look at a couple of different combinations of these things using this disjunctive or and this exclusive or right here. So in particular, if we were to look at P XOR Q, well, P XOR Q, either one is true or the other is true, but not both. Well, P is true. Yes, my name is David. Q is not true because my name is not Sam. So this thing right here is true. But if we were to look at the disjunctive or instead, P or Q right here, well, it's P or Q. This takes on the truth value when either one of them are true, but not both. Okay, so in this case, P is true, Q is false. That's fine. This compound expression has a truth value of true. But let's go ahead and contrast that to the following. Let's look at P XOR R. So P XOR R, remember P, that's my name is David. That's true. R, PSU offers Computer Science 360. That is also true. Well, the exclusive OR, XOR, says that this statement right here is going to be false because both of these right here are true. So this is false. Whereas the disjunctive OR over here, if we did P or R, well, that doesn't care if they're both true or not, right? Right here in the definition, it says either P or Q or both are true. So in this case, this is going to take the truth value of true right here. These are basic logical operators. Not, and, or, and XOR. From these, we can build much more complicated compound expressions. And we're going to see one more implication a little bit later on and relate it back to these basic building blocks of these logical operators that allow us to build up more complicated logical expressions.